Hello, AP Chem students, and welcome to topic 3.12, properties of photons. The learning objective for today is 3.12.a, explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. So let's talk about it. So photons, remember that when a photon is absorbed by a substance, the energy of that substance is increased by the amount of energy in the photon. So when elements are exposed to light in the visible or UV spectrum, it excites the electrons, causing them to jump to a higher energy level. And I'm going to move my head, and hopefully that doesn't mess up my recording. Let's see. Yay. Okay. In looking at atoms and where their electrons are located, we can determine if an atom is in the excited state or the ground state. So let's compare those things side by side. So the ground state is the most stable arrangement, which has the lowest energy, right? Because nature finds stability at the lowest energy, versus an excited state, which is an electron configuration at a higher energy resulting from the absorption of energy. So what does this look like? So for a Bohr model, for boron, you might see the ground state look like this. And remember that an electron configuration of boron in its ground state would be 1s2, 2s2, 2p1. Whereas in the excited state, we might see it look like this: 1s2, 2s1, 2p1, 3s1. So you see that we have an electron that's been promoted, okay? So you just kind of see it look like it's out of place. So here's another way to show that with an Aufbau diagram with beryllium. So you can see we've got a ground state beryllium atom here. We're following all the principles that we would expect it to follow in terms of filling of electrons being filled with lowest energy first and then moving up from there. Whereas here we have a beryllium atom in the excited state where we have 2 electrons in the inner level, the inner energy level, excuse me, 1 in the 2s, and then 1 that's been promoted to the 2p. So again, it just kind of, you can tell it's in the excited state because you have, generally the easiest way to see it is kind of an not completely filled inner sublevel, and then an electron that's gone ahead and moved what would look prematurely into a higher energy sublevel. Okay, so light behaves in a way that's unusual for us to think about because it simultaneously, behaves as both a particle and as a wave. So that tendency of light to behave in these two ways is called wave-particle duality, and it means that light has some properties of both behaviors. So we're going to examine both parts of that. So with wave-particle duality, we actually have experiments that show that this is the case. So the first one is called the double slit experiment, and that's a situation where you put a light source or electrons, it can be electrons as well, aim it at a barrier that's got 2 slits in it. And then when they come out on the other side, you see this pattern that matches a wave, which is interesting because you've got these 2 slits, and so they're coming through that and acting as a wave. So you see this wave pattern distribution. However, if you take a light source and you aim it at the surface of a substance, it's generally done with a metal, then what we see here is instead of seeing all the energies emitted back in the form of a wave, we see only electrons at specific energies, so these photoelectrons. And so that is evidence of light as a particle, because if all of this was being absorbed as a wave, we would expect to see a wave come back out. Okay, so light has the characteristics of a wave. It has speed, which is represented as c. It has wavelength, which is represented with a lowercase Greek lambda, which looks like this. And then we've got frequency. I know that looks like a V, but it's actually the lowercase Greek letter nu. The distinction is not showing up very well in PowerPoint today. So often the V kind of has like a hook at the end and a slightly rounded top up here. But this is on the equation sheet, which I'm about to show you. So light can move through a vacuum, and it has a set speed that's denoted by c. So this is the speed of light through a vacuum, 2.998 times 10 to the 8th meters per second. And this allows us to see the inverse relationship between wavelength and frequency. And I love this video. It shows it so nicely. If you have a higher frequency, which means you have more waves passing a point in a given time, then you have a smaller wavelength, which you can see here. This is squished. versus if you have less frequency, then you have a larger wavelength. Okay. And then what's interesting about this video is it might look like this red ball is actually traveling faster. But if you look at both, the speed at which it's traveling is the same. So it's going to the same position on the video every time. All these red things are in line with each other. And so the speed is the same, even though it might not look like it. All right, so then here's your equation. So C is that speed of light, and here is your, oh, my graphic got messed up here. This is wavelength, and this is frequency. So let me fix that for you. Okay, there we go. So speed of light, wavelength, and frequency. Okay, so now I want to show you that this is, of course, on the equation sheet. So we're on the equation sheet, and now we're in this atomic structure section again. Here is the speed of light equation, and then here are the definitions: frequency, wavelength, and then here is your speed of light value. My little purple box is out of place here, but you can see it there. Before the 20th century, it was thought that energy always acted as a wave, and therefore matter could absorb or emit any amount of energy. In 1900, Max Planck gathered data that disproved this. So his data did not fit the then accepted ideas, and I've heard that even he didn't believe it at first, but he explained his data and announced that energy could only be gained or released in discrete amounts called quanta. So his ideas developed the following equation, and with it came a new constant that they named in his honor. So this value of H is a constant that's called Planck's constant. So it's 6.626 times 10 to the negative 34th joules times second. And that allows us to relate energy and frequency via this equation. Now, as before, this equation is on the equation sheet. So this relates the amount of energy, which is a particle property, and frequency, which is a wave property, relate. So there you go. Now, I want to point out to you that frequency is in both of these equations. So you can actually translate wavelength to energy and vice versa by going through frequency. Okay? And so you would just do both equations. You would go from wavelength to frequency, frequency to energy. Or you could go energy to frequency and then frequency to wavelength. All right, so wave-particle duality. It makes sense that if a wave can have the properties of matter, then matter can also have the properties of a wave. And that's called wave-particle duality. So Louis de Broglie described this in 1923. And we now recognize that all matter exhibits both wave and particle properties. It's just that that can be a little fuzzy for us because we are so relatively large that any wave properties that we have as, human particles are so small that they're undetectable. And they don't impact us and we don't notice them at all. But if you go much smaller in terms of your size, then you start to see the properties of both. So that's kind of where I think a lot of people have a hard time with it because this seems to not fit our reality. But you got to keep in mind that quantum mechanics is at such a smaller scale than we're used to thinking about. So it is different than what seems like reality to you. Okay, so what should I be able to do with this? Well, first of all, given the wavelength or frequency of a photon, be able to calculate the other factor using C equals lambda nu. Given the energy or frequency of a photon, be able to calculate the other factor using E is equal to H nu, and then use frequency as the common factor to convert between wavelength and energy of a photon. So generally, this happens in terms of calculations. Sometimes we do see questions that say, like, if you have a wavelength of X and a wavelength of Y, which one would be the higher energy? And then you don't necessarily have to do a calculation. You can just reason through it with proportions. But that's it. And I will see you soon for the very last section of Unit 3.